Welcome to the Crazy Hat Chemist. So today we're doing another video on atomic structure and electron configuration. So let's get moving. Bam! So today we're going to be talking about the physics of waves. Okay, most subatomic particles behave as particles. Some behave as waves and obey the physics of waves. Therefore, we are studying the physics of waves. Okay, here are some properties of waves of which you absolutely need to know before we get into the physics of waves. One is the wavelength. Okay, that is a lambda. Okay, that is that symbol right there. That Greek letter is the lambda. It is the distance between two identical points. Generally, they're two identical troughs or two identical peaks, but it could be two identical points anywhere along the wave, and that would be the wavelength. The frequency, and that is nu, that is a scripted like V like a thing, and that is the number of complete waves, that is cycles, passing a fixed point in time. So that is cycles per second, and you can view that as hertz. Like if you are familiar with an old radio, you should see on the radio dial they are hertz, or maybe megahertz, or something like that. Then there is the amplitude, and amplitude is the maximum height of a wave. Okay, then there are nodes, or a node. And a node, or a nodes, is the point where there is zero amplitude and occur at half the wavelength intervals. Okay? A standing wave, or a stationary wave, and here are some characteristics of a standing or stationary wave. And this is going to be very important in looking at the atom and the next model of the atom when dealing with standing waves. There are two or more points where there is no movement, i.e. there are nodes, and that is the amplitude is zero at these nodes. So think about a violin string. A violin string is fixed at two ends. Each of those ends is a node, and then as you pluck that string, then you will get certain parts of that string to vibrate. If you place your finger along that string, that would also be another node, of which would be a third node on that violin string in total. Okay, the nodes are located at n, the n times the wavelength over 2, where n are whole positive integers, 1, 2, 3, 4, 5, 6, 7. That's going to play a very important role here in just a moment. This is an example of the quantization, of energy, okay, a concept important to electrons and atoms in the quantum wave mechanical model of the atom, which we're going to be discussing here in a little bit. Not today, but pretty soon. Okay, so here's a picture of three waves here. I have a purple wave, I have an orange wave, and I have a red wave here. Okay, so here is the wavelength of the purple one, and you can find that this wavelength is the same anywhere along this wave. You could take two successive points along this wave, and I picked two successive troughs. That is the lower portion of the wave. Here is a wavelength on the orange wave, and that is two successive troughs as well. I could have picked the peaks as well, but anywhere along here would give the same wavelength. The wavelength for the red one is not on here because there's not a whole complete wave on this slide that I have here for it. It actually continues further. This is an amplitude. This is the maximum height that this wave reaches. And this is the same amplitude for all the waves on this slide here, whether it's the purple light, the orange light, or the red light. It's the same amplitude. That's the maximum height of that wave. And here are some nodes. This is a node where the purple wave is and the orange wave, and then another one for the purple wave. Okay, that is a node is where there is zero amplitude for that wave. Okay, and red light has a long wavelength, low energy, and a low frequency. However, violet light has a short wavelength, high energy, and high frequency. And I'm going to write this down right here, right above. So notice that that's in red. So red light, visible light, that is, has a long wavelength. I don't even have a complete cycle on this slide here for the red wavelength of light. Okay, and it has low energy and low frequency. You can see that not a lot of them pass through this whole entire section of this slide. And this is opposed to violet light. Okay, violet light has a very short wavelength. Notice on this slide that the red wavelength is so big that it's not incorporated in this slide. The orange wavelength is then not as long as the red wavelength, and then the violet light is even shorter in wavelength. Okay, there is high energy in the violet light. There's high frequency. Notice that there are more waves passing within this given amount of time with the violet light than the orange light, for example, which there are fewer waves passing in that given amount of time. That would be the cycles per second, that would be the hertz. So that's why the frequency is high for the violet light, because there are many waves passing within this given amount of time. Okay? So why study atomic structure? So it's really important because every 4th of July or every time you see fireworks, you should be looking at not just the colors themselves, but beyond the colors. And beyond the colors, you should be thinking about the elements of which are on the periodic table. Okay, so when you see violet light, you should be thinking strontium and copper combined. Okay, when you see green light, you're going to think either barium or boron. And when it's orange light that you see, you're going to be thinking calcium metal. Okay, and then here are some more fireworks. This is silver, and that is either superheated magnesium or superheated aluminum. Will give you that silverly bright color. Okay, and blue light is going to be copper only, and red light is going to be strontium. It's one of my favorite ones there. Okay, and here are some more. Yellow is going to be sodium. Sodium is really important because it blocks out pretty much all the other ones, and you need a piece of blue cobalt glass in order to see other elements like potassium. White is going to be magnesium, aluminum, or titanium. And then right over here is this 1927 conference, and the title of the conference was Electrons and Photons. 17 of 29 of these became Nobel Prize recipients. That is amazing. Absolutely amazing. So I want to point out some of these Nobel Prize recipients with these shadows of light here. So you see that they are all over here. Incredible scientists at the time. Okay, in 1927, these all got together. I want you to point out one thing. There is one female in here. Okay, that female is the only one with 2 Nobel Prizes. There are some great individuals here. Okay, and I'm going to point out a few names of which are essential to this entire unit, which throughout this entire unit, we're going to be talking about many of these people. And these people are essential to this whole unit on atomic structure and electron configurations. So one of them is Erwin Schrödinger. Another one is Pauli. And the other one is Heisenberg. And Planck, Marie Curie. She's the only female here. The only one also to have 2 Nobel Prizes, 2 different times in 2 different fields, chemistry and physics. Okay, Albert Einstein, of course. And Louis de Broglie. And, of course, Niels Bohr. So I want you to look at these individuals. They play essential roles in the development of this entire unit of atomic structure and electron configurations. They are essential. Okay, that was another video here, and I am the Crazy Head Chemist, and hopefully you can see my taco. I don't know if it's a Tuesday or not in your neck of the woods or when you're watching this video. Give me a thumbs up if you like the video. Give me a thumbs up if you like the hat. Okay, and subscribe to my YouTube channel, and I'm going to see you next time for another great, awesome chemistry video. See you next time. Bye now.